until recently, so I do not have proper transparencies. This is work in progress, and since some of the formulas would take more than I want to write, I will use the manuscript of this paper. Well, this lecture will have two parts. The first part will be a brief introduction to Spinors, because, as one says often, there are young people in the audience and they should be introduced to this beautiful concept. Everybody knows something about Spinors, but since I want to use them in the second part of this lecture, I will give this brief introduction. What are Spinors? They are the fundamental representations of the Lorentz group. Well, they are very simple objects, and my notation is the one that is used in general relativity, namely the components are denoted by capital Latin letters, because Greek letters have been used for relativistic vectors. Latin small indices are used for space parts, and we are left now with capital Latin letters. Spinor has two components, and there is a tradition to denote these components by 0 and 1 that is used in general relativity. How do they transform? Mathematically speaking, they transform according to SL2C. Group of matrices. In plain language, that means that they are transformed by 2 by 2 complex matrices, and S stands for determinant equal to 1. So this is how they transform, but that is not sufficient to deal with Spinors. We must also have some structure, and this structure is kind of metric. It's not quite metric because it's anti-symmetric, but it is still used to raise and lower indices. The indices are raised according to the following rule. Psi A is epsilon A B psi B, and they are lower because of this anti-symmetry. There is a change of sign, so it is customary to write down this by the following formula. Psi B equals psi A epsilon A. So the rule is we raise the indices in front and we lower them.
And epsilon super AD is equal to epsilon?
Yes, this will be, okay, I can, epsilon super AD is the same as, and this is of course in agreement with this rule. Now, there is an important structure here, since, as I said, Spinors are representatives of they are vectors on which the representations of Lorentz group act. Therefore, there must be some nice connection between ordinary vectors and Spinors. And this correspondence has been really extended, perhaps even too far, by Roger Penrose, who in a way identified the vectors with Spinors, never worrying about the translation between the two. I am old-fashioned. Well, Roger Penrose is about my age also, so that's not saying much, but I use, as a physicist, I don't like these shortcuts too much, so I want to have everything in plain language. There are objects which have vector indices and Spinor indices. Now there is this A dot. What does it mean? There are two inequivalent representations, two-dimensional representations, and they are simply related. One is the complex conjugate of the other. And those objects in the Spinor formalism that transform according to the representation, which is complex conjugate, are denoted by A dot. Since this was started before the era of LaTeX, Penrose and others could not convince the printers to put dots because that would require a special font. Instead, they put commas here, but I like dots. Now there's no problem, you just write / dot and it's printed like a regular dot. Okay. So what are these objects?
I believe the Van der Waalen used the A dot notation.
Yes,
Because at that time,
but
the printers were doing what they were asked.
yes.
They were not
They
complaining.
did not have
They were
powerful.
No, they were not complaining because they were the good
Yes, but
French or
but
German.
they used small Greek letters.
That's true. That's true.
So what is this object? This is a connection between spinors and vectors. What does it mean? If you transform this according to the spinor representation with respect to indices A and B, and also with respect to vector representation of with respect to this index, this object is invariant, the same way that G mu nu is invariant under Lorentz transformation. So we have these objects and they are very, very useful. We can raise and lower indices, and I will also need the one that is the following one, A, B, diagram. How do these objects look like? They're very simple when you write them in terms of familiar Pauli matrices, namely G mu A, B. When you substitute for me 0, 1, 2, 3 is given by the following set of matrices: unit matrix and sigma Pauli matrices for the remaining 3 indices. What about this other one? The other one, G mu AB, is again very similar, unit matrix and minus Pauli matrices. With these objects, one can form more complicated objects by contracting the indices. The contraction rule. Są jeszcze jakieś krzesła tutaj wolne?
Tu są.
Chyba że pan chce wyjść w pewnym momencie. So there is an object which I will need, and you will see why, which is constructed from G mu AB object. And this object is S mu nu. I write it with indices downstairs, AB. And this is defined as 1/2 G mu. Really, how do I want to write it? No, yes, I need something more. Epsilon AB, I want to raise this index AC, epsilon AC, 1/2. Now G mu CD, G nu DB, minus the part which has mu and nu interchange. So this is G nu CD and G mu dB. Obviously, this object is anti-symmetric in the indices mu and nu, and it turns out that it is symmetric. You can check in indices AB, and it is again a combination of Pauli matrices, nothing more. So that much for the spinorial formalism. And why do I need the spinorial formalism? You will see very quickly. Namely, having this object S mu nu AB, I can go freely from spinorial space to the ordinary vector space for the electromagnetic field. Namely, I can define the following object now,
Excuse me, and what remaining, what is the symmetric part, symmetric traceless part of S?
Is delta.
Is that?
Is delta. Symmetric part is delta, and asymmetric part is this S. Now, what is the basic formula that I will use? Once you can go freely from the standard notation for the electromagnetic field and the spinorial notation, you can write the following formula. F mu nu equals S mu nu A B and some spinor phi A B. Since this is symmetric, phi A B must also be symmetric because the anti-symmetric part will not contribute here. Now, how many components F mu nu has? F mu nu has 6 independent components, and the symmetric 2 by 2 matrix also has complex matrix, has also 6 components, so every electromagnetic field can be represented in this form. Why is this useful? Now we come to the main topic of this seminar. This is useful because it's much easier to work with Maxwell equations, as you will see, in the language of phi AB than it is in the language of F mu nu. What are Maxwell equations in terms of phi AB? I will show you here. These are Maxwell equations. They have the following form. G mu A. I can use the same letter because A dot is a different index. Now the derivative mu contracted with this index mu, acting of phi A equals 0. These are Maxwell equations. All Maxwell equations are equivalent to this. You have to translate phi A.
Without charges, though. Without charges.
Yes, yes.
Of course, free
Free.
Free Maxwell equations. It will all be about free Maxwell equations. Not only this, but the topic of my seminar is about gravitational waves. This holds for any equation for symmetric spinors if they represent massless particles. So in a general case, we have the same form of the equations. Phi A, B, dots, 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 L, d mu equals 0. For Maxwell equations, we have 2 indices. For neutrinos, if they were massless, there would be just 1 index. They are not massless, as we know. Now, and this is for any number of indices. In particular, this will be the case that I will be interested in. For gravitons, it's A, B, C, D. Why there are 4 indices? Because each index here contributes spin 1/2. So in order to have photons, we need 2 indices, 2 1/2, it's 1. And if we want gravitons, we need 4 such indices. I think this is about all I wanted to say in the introduction, and now we come to the real stuff. And what is now here is at the bottom. Maybe I should enlarge this because this is a very important formula. Even 125 will be proper. Look at this formula at the very bottom. What do we have here? We have symmetric spinor field now, which is everywhere in space-time. And on the right-hand side, we have our familiar objects. G mu AA contracted with delta mu. So that's the same object. It's sort of derivative translated into the spinorial formalism. And we have a repetition of such constructs here each time we have this, we have also sigma A, which is a constant spinor. Constant spinor that is just a set of two numbers. And at the very end of this equation, there is a function chi. Now, a theorem proved by Penrose is that in 1956 is the following. Every
this phi is potential.
Tak jest.
chi,
Super, super.
super, the chi
Yeah,
is
there
a
is
super.
this disturbing
I
duty.
cannot use the word superpotential because this was taken over by supersymmetry people. And they don't allow anybody else to use it for a different
But
purpose.
that's a free word.
No, there are patent laws. That would be a patent infringement. Anyhow,
I doubt.
Penrose
Do they
proved,
have a Polish patent?
Penrose proved that for every solution of the scalar field equation, ordinary scalar field D'Alembert equation, chi equals 0. Chi is a complex field. This is a solution of this equation, which is very easy to check. That's an exercise for students. What is difficult is to prove that every solution of this equation can be written in this form. That requires some technical assumptions about the connectedness of the space, etc. I will not go into it because I will deal with flat Minkowski space. And what about this spinor sigma? If I change the spinor sigma, that simply means a Lorentz transformation of this field. So I can choose any spinor, and then if I want to transform it, that is equivalent to changing sigma. And what is the simplest choice of sigma? Of course, the simplest choice of sigma A is equal to 1, 0. It has only one component, and this component is 1. If I would change it into something else, that would just rescale the whole field. Now, notice one.
Is it very easy to see that the right-hand side is symmetric in A, B, C, D?
Yes, because derivatives are symmetric,
Okay, so
and because
So whatever is
So whatever-
less is all
yeah.
the symmetric.
all these apparatus, differential operators commute. So this is a symmetric object. Now, what is the purpose of this exercise? It establishes a very simple connection between solutions of various equations. I can choose one function chi and have a solution for neutrino, for photon, and for gravitons. Therefore, if we know some solutions that we like, and I will talk about these solutions in a moment, we can immediately write the counterparts of this solution for a different field. And this paper that is being now written was in a way triggered by work by Steve Burnett, who also wanted to establish a correspondence between electricity, magnetism, and gravitation, but he didn't do it right. Because his idea was that A mu, the potential in electromagnetism, corresponds to G mu. The G mu is like the potential. And then he tried to work out the correspondence. Why this is wrong? Because A mu differentiated gives F mu nu, which is a geometric object. But derivatives of G mu nu are not geometric, they are parts of Christoffel symbols, and of course
Which is also a geometric object, but of completely, but non-tensorial.
non-tensorial, which is much worse than tensorial objects.
Not worse, it's different. It's just a different geometric object.
Okay.
Beautiful geometric.
Well, but the Christopher is almost as bad as Mephistopheles. So we don't like
So what is the answer to the question, what is the correspondence between electromagnetism and gravity in this language? The correspondence is that F nu nu corresponds to the Riemann tensor, or in this context, the Weil tensor, because by definition, the Ricci tensor vanishes for this linear case, and this correspondence has a tensorial nature, and moreover, it works for the solutions that we want to establish. Okay, so now what we do with this observation. By the way, the idea of introducing some superpotentials goes back to Hertz. Hertz potentials are of this category, and there are many people who contribute to this. John Stewart, a relativist, searched the history, and he proposed the name for these potentials, which goes like this, if I can properly remember. This is H, V, D, W, P. H for Hertz, B for mathematical physicist Bromwich, D for Debye, W for Whittaker, and P for Penrose. So the Penrose's construction is the most elegant, because other people were not using Spinors and they were just reshuffling the derivatives. So this is the gallery of people who contribute to this, everybody in its own way, but in this Spinorial language it is really extremely simple.
May I make a comment?
Yes.
Not every solution is of that form, but is a combination of solutions of that form. Because
No, every solution is in this.
no, because if you must combine these expressions for different spinors. You may say that this is a tensor product of those sigmas and tensor.
No, every solution of Maxwell, let's talk about Maxwell equations. And I will comment on that. Every solution of Maxwell equations has this form. There is a phi,
For Maxwell
there is a chi
equations,
for Max, and for gravity it's the same. Absolutely the same.
I
You will
can
see.
understand. So
Okay.
you claim that if I have a solution of linearized
Gravity.
gravity, then there is a unique choice of those sigmas, and there are 4 of them. And
No. Sigmas, no. Sigma is a constant.
Spinor.
yes, it is a constant.
Yeah, but all of the sigmas are the same. There's just one sigma which is related to fixing the Lorentz frame, so to speak. I will comment on that in a moment. So, what is being done next? Well, this is here is this combination which enters here all the time, and every phi a, b, etc., is just obtained by acting several times with this operation and several times with this operation. So the general formula for the components of phi, every component has this form, is written here. Phi, which has a certain number of, well, I may even have this gadget here, you maybe need to point. Well, every component, because this is symmetric, it's enough to take sort of normal ordering, zeros in front and ones in the back, has this form. If there are L zeros, then we have dt minus dz to the nth power, and minus dx minus dy to the nth power, standing for the index 1. So we now can go to the electromagnetic case before we move to the gravitational case. Use this definition and see even better what is the relation. Of course I cheated. I should have written F mu here. And the real part, yes, yes. The real part of F mu nu is ordinary F mu nu. Here's the definition. F mu nu is equal to F mu nu plus I epsilon 1/2.
Yes.
Oh.
There is formula number one
Yes,
something.
yeah, sure. So this is F mu nu because it's complex, and complex has redundant components. We can get the real part, the real field by taking the. And of course, this is connected with the Riemann-Zilberstein vector, which we like, etc. Sorry for this omission, but now it's straightened out. And now, what are the components? What are the relations between the components of the Riemann-Zilberstein vector, which are simply E times IB? Well, they're a combination of these phi's. So this is simple algebra. Now we go to the gravitational field. Things are a bit more complicated, but not too much. And instead of introducing, instead of working with the Riemann tensor, we form a complex combination which plays the same role as the Riemann-Zilberstein vector, and G mu nu, the complexified Riemann tensor, is just a combination of the components of this 4-rank spinor. So now we proceed, and we now want to do something interesting and new. By the way, this construction of making Riemann tensor components complex is not new. It has been used by relativists. We have a combination of some parts of the Riemann tensor which are claimed to be analogous to the electric field, and the imaginary part which is claimed. This has been recently picked up by many people. There's a very long and exhaustive paper by Kip Thorne and his associates, which deals with this analogy at the level of the Riemann tensor. They even have some geometric interpretation of E and B. One is called the share part, and that is not very important for me, because now I come to the practical use of these formulas. And the practical use is the following. There are many solutions of Maxwell equations now which have become popular because they have intricate properties, and these are solutions that carry orbital angular momentum. As we heard here from both Tide, there are expectations that this will improve the information transfer because we open new resources, as it is now called, resources for storing and transmitting information. And these resources are in the angular momentum dependence. Why these are new resources? Because you can have one frequency, which is given to you by some regulatory agency, and you put into this one frequency, or into one band, a lot more structure than it's usually done, because you can have the same frequency, but many different orbital momenta. And one active group working on this is one in Vienna under Zeilinger. They already had practical confirmation that this is really a new thing, that they transfer information using one wave frequency, but various angular momentum components. So that is why angular momentum is becoming even more popular. It became popular some time ago when people discovered in optics that they can use angular momentum to manipulate micro-objects. Like, for example, bacteria or other things under the seen under the microscope can be manipulated with angular momentum, which gives a twist to these micro objects, because it carries angular momentum. So, the most popular beam that carries angular momentum is Bessel beam. Bessel beam has been known for many, many years. I don't even know who was the first who discovered this beam. That might have even been in 19th century.
Might be even Bessel.
No, not Bessel.
Bessel is not discovered.
Bessel was not interested in Maxwell equations. Okay, anyhow, now what is the choice that seems to be most natural for the function chi? Of course, it's a solution of D'Alembert equation of the Bessel type. It's the solution which has angular momentum m. And once we have this solution, now it's a trivial game to differentiate this solution. And the beauty of this is that Bessels are nice. It turns out that when they are differentiated, anything that happens is to lower the index of the Bessel. This particular combination of derivatives, dx plus I dy, just forms a ladder of Bessels and repeat. So what do we get here? The simplest way to obtain Bessel beam. If you wanted to do it by a straightforward solution of Maxwell equations, you will be surprised how much work you need to put into this. And here, all you have to do is to differentiate the Bessel functions, and the formulas are, as I said, very simple. All you get is either lower or raise the index. And now what is nice is that this solution of Maxwell equations is an eigenstate of the angular momentum, total angular momentum, that belongs to the value capital M, and capital M is little m, which is the orbital part, and 1, which is the part contributed by helicity. So we have a nice way. Now, of course, there's some algebraic work that you have to do. You can use Mathematica for that. You have to go from phi 0, 0 to f, and then you have to separate the real and imaginary part, and these are all routine operations. So now I am even afraid that you will find it entirely trivial. You can do, again, absolutely the same for gravitons. You use the same chi, and you repeat the derivatives.
There is a more derivatives.
More derivatives, but look at the end. At the end, this is not any more complicated, except that there are more components here. And from these components, if you like, you can take the real part at the end and the imaginary part, and you have all the components of the Riemann tensor. Now, this is, of course, just one example, but you can take anything you want for chi, which solves the D'Alembert equation, differentiate. Sometimes the differentiation may be not trivial if you take your formula for chi too complicated, and you arrive at the final solution. Now I would like to address the question raised by Professor Kiosk.
I have a similar question. In a real notation, if you will use a proper unit, what would be the velocity multiplying wave vector k?
Well, I put everywhere c equals 1.
That c, there will be c in
Yes.
gravitational case?
Yes, because this is linear gravity. Minkowski
It's
metric.
linear
So,
on
no, it's okay.
the Minkowski background.
Yeah. Okay, so
May I
now,
put my question in different words?
no, let me first answer your question in the original form. They mean
But he's no longer
when chi is a solution
Mhm.
of D'Alembert equation. Therefore, it can be written in the form of k divided by k e to the minus I omega t plus I k r, some amplitude f, of, I call it f plus e to the plus I omega t minus I k r times some amplitude f minus of k, which I like to introduce with a star because these are nothing else but the wave functions of photons in momentum space. Now, since we know that every solution, I'm not talking about some bizarre cases, but every solution of D'Alembert equation can be expanded into plane waves because they form a complete set. Therefore, if I do this, and I, now in the Maxwell case, I use these derivatives, what do derivatives do? The derivatives introduce components of the k vector and the omega. So what I get here, after applying these derivatives, is the following formula. F mu nu, this complexified vector of the electromagnetic field, will be equal d3k over k. Here's some combination of the components of the k vector, E mu nu, which I call E mu nu of k, and times the same thing here. Now this is the standard representation of every electromagnetic field with the polarization vectors which are here made into relativistic objects. Does this answer your question?
Because not every electromagnetic wave is polarized. It may be split into polarization.
Of course.
Yeah.
There are two every electromagnetic field is a combination of two polarizations. This polarization and this polarization.
This is precisely what I...
No, because this is chi, which does not have to, it already contains both polarizations. One chi carries both polarizations.
Okay, maybe I'm missing something, but the space of solutions of each of these equations is linear. If you have two solutions, the sum is
Yes.
also is a... Okay, now if you write down your solution in terms of 1 sigma,
Yes.
and you perform the Lorentz transformation,
You just transform it.
you get another solution. Now the sum of these two can be written in terms of a single sigma, because you have something with 1 sigma plus something with another different, because sigma doesn't enter in a linear way in your formula.
Sigma is just an auxiliary variable which
of
fixes the frame of reference, which sort of separates electric from magnetic field because in general they mix.
Yes, I agree. But if you perform Lorentz transformations, it is equivalent to the change of sigma.
Yes.
Now take two such solutions.
Why? I have most general solution. Why do I have to bother with taking the sum? This is the most general chi I can write, assuming some regularity conditions.
Yeah.
And my statement is every solution of Maxwell equation has the form that I have written before, with some chi, and if I want my photons to have wave functions f plus and f minus, then I choose this particular chi, and it gives me what I wanted. Two polarizations.
What Jurek is asking is to take two such solutions and demonstrate that you can write them as one.
Because you can still use your formula for 1 sigma. You may add another solution, maybe even for different sigmas. And I am missing the following point, that the sum of two such solutions may be gathered into a single solution with a particular sigma, because sigma doesn't enter in your formula in a linear way. Maybe I am wrong, but I would like to understand this.
You said that I need linear combinations of my solution. If I take a linear...
No, I didn't say... I suppose I take a superposition of two such solutions. So I would like to understand
it amounts to adding f plus 1 plus f plus 2 and f minus 1 plus f minus 2.
Okay,
That's all.
this is precisely the point which I do not understand, because if I phrase this, my question in terms of your sigmas, then I would like to understand how can you reorganize a sum corresponding to two different sigmas?
I don't care about different sigmas. I'm claiming that for a fixed sigma, I get everything.
The point is that
That's
the
it.
superposition is done on the level of this field,
That's right.
not on the level of this
I
phi.
don't care about sigmas.
And therefore,
Sigma,
on the level of phi.
Yeah,
Sigma
but still it should be possible.
yes.
But
Sigma is chosen once forever as 1, 0. That's it. I'm
Just
not
have
going
to solve
to
more
change sigma, and I claim
equations.
that every solution of Maxwell equations has this form with my fixed sigma.
But it means that it should be possible to rearrange this
absolutely.
Of course.
product.
Yeah, sure.
If we Lorentz
And this is
the
real.
sigma and the function chi as a function, we
Yes.
should get the same thing.
Yes,
Exactly.
exactly. That's
So it's equivariant.
how I called it Lorentz transformation.
So we could choose one sigma once and for all solutions. And
Notice that all indices match. All spin. Therefore, it's all invariant under Lorentz transformations. If I transform sigma under a Lorentz
they act both on
transformation.
sigma and on the function chi. As a-
So I wouldn't like to prolong this discussion, but there is still a problem which I am unable to understand at the moment, that I would like to understand it. Namely, written as you did, the formula is valid for different sigmas.
Yes.
So
But
when
still,
you
by
take
changing
sum-
but still by changing the high, you can change the sigma to the same sigma
Exactly.
of another solution.
Mhm.
And this is the way how you can.
Sigma niech numeruje rozwiązać.
First, you have two different sigmas, yes? But then, by changing the high of one of them, you can change the sigma to the proper one. And this is how you can do
Now
it.
to end this, I would like to
Cała fizyka jest potencjalna.
I would like to go to Wigner in 1939. Wigner wrote a very nice mathematical paper where he enumerated all unitary representations of the Poincaré group. By the way, we often are not happy that it takes too long to publish something, and Wigner's paper was sent to mathematical annals in 37 in December, but still in 37 it was published in 39. So either Wigner had enemies at the editorial board, or the process then took over a year, even though it was Wigner. So what did Wigner do, and how is this connected with what we are doing? Wigner classified all representations of the Poincaré group, and among these representations are the massless particles, like photon, graviton, and perhaps scalar or neutrino. And according to his classification, these particles, massless particles, are described by one-dimensional, in momentum space, of course, one-dimensional representation. What does it mean that it's a one-dimensional? That means that it can only pick up a factor. Because it's a unitary representation, it can only pick up a phase. So in this classification, Wigner has shown that massless particles of helicity h, photon has helicity 1, graviton has helicity 2, and lambda is the sign of helicity. The transformation of these wave functions of the photons must be of this simple form. And how does this compare with what we are doing? Well, we have the same f's here in the Fourier expansion, and since the whole structure, as you see, is relativistic, because d3k over k is relativistically invariant, it's not clear how it comes out to be invariant, because here we have three vectors which we would think spoil the symmetry between space and time, and here we have the modulus of k. There is a very simple trick to convince those who do not believe, namely, you can write this formula as a four-dimensional integral, and and delta function of k squared, and then it amounts to the same and proves that this is a relativistic part. Of course, this is also relativistic because we have k dot x, and therefore f can only transform according to Wigner, and this is how every solution of Maxwell equations has the photon interpretation. Instead of saying that the wave is such and such, we can say that the wave function of the photon is such and such. And of course, one can easily work out, and we did it some years ago, what is f for Bessel functions and for Laguerre-Gauss beams and for other beams. One can write down all these solutions which are interesting in terms of photon wave function. Well, I think I have finished. I hope there are some questions. Does that mean that everything is obvious? If so, I'm happy that I convinced everybody. Now, this is really very simple. It should be taught in elementary electricity and magnetism, that one can write solutions of Maxwell equations. There's a lot of, if you take any textbook on electromagnetism, even for plane waves, you have to struggle a bit. But if you take something much more complicated, before you get to Bessel equations, you have various components, you eliminate one component, the equations, how it is done. The equations of Maxwell are first order. Then you have to go to the second order equation because Bessel functions satisfy the second order equation. So you eliminate some components. You have to worry also that the divergence of the field is zero. So it's a mess. But here it's just a plain series of steps. You have one scalar function and then you develop it by differentiating into more complicated objects.
But it is not the only way, there are many other ways too.
Oh, sure. That's why there are so many names associated with this, but the Penrose construction is, in my mind, the simplest one.
For some purposes.
For, at least for the construction of Bessel beams, for example. Because it comes out very nicely for the Bessel beams. If there are no more.
But if we have charges or
It
currents,
is three.
is something similar
Oh,
to write the green function,
Hello, Giovanni.
the solution of infinite.
Yes, I have 5 minutes. I want to show you something.
Absolutely.
Of course. I have completely forgotten
Empty space.
that I.
Bez ośrodka, bez źródeł, bez źródeł.
A jak sądzisz?
Ale oddziaływanie to już jest nie...
No to już potensja.
To już jest nie...
Dobrze, ale mam sobie rozwiązanie.
Here is an illustration of the correspondence between electricity and magnetism. What is this? This is the distribution of the energy in the plane perpendicular to the propagation direction for the electromagnetic field. So we take
The Bessel beam.
Or the Bessel beam. Which beam? M equals 0.
Of course.
Now let me put M equals 1, which is more interesting, and then Mathematica calculates, and this is the reason we like Bessel beams, because they have this wavy structure which can carry some information. Now we go to gravity. There is no energy, there is no local energy density for gravity. So what is this for zero Bessel beam? This is what is called super energy.
Of course.
Super energy is built from Bell-Robinson tensor. And how it is explained in terms of spinors, it's very simple. What is the energy density for the electromagnetic field when you do it in spinorial components? You take modulus squared of this, and you take a sum over A and B. And this is the energy density. So you can do the same, you can take F, A, B, C, D, modulus squared, and sum over all indices, and you get a scalar three-dimensional scalar, which is always positive definite, so it is like the energy, and it's local, so we can plot it. And this is the plot of this object for m equals 0. So let's see what happens if this is for. So let me now put m equals 1 and ask Mathematica to do it. The same thing. So you see a great similarity between these two waves. The Bessel beam for the electromagnetic field, the Bessel beams.
Could you trap something inside?
I would have to generate the gravitational wave first without carrying angular momentum. And that's an interesting topic in itself, to imagine some sources that would produce these Bessel-like gravitational fields, and then we can worry about dropping something inside. Okay, so that is my illustration of Bessel fields for the gravitational field. Thank you.